Hey everyone, welcome back to my podcast, Anatomy and Physiology Bit by Bit. This is your host, Dr. Steve Sullivan, and I am coming to you from just outside of Philadelphia, where I've been teaching anatomy and physiology since 2002. Today's episode, we're going to continue on with the urinary system, and we're going to specifically discuss the nephron, which is the functional unit of the kidney. Just a quick little side note here. I want you to check out my Instagram account, Student Help 4AP, that's the number 4, the letters AP, and check out my recent post with images of the nephron. I think these will help you follow along with today's episode. We'll talk about how blood plasma is filtered into the nephron and what happens to it while it's in there. Before we get to that, I want to answer a listener question. I got an email from Ben from the United Kingdom, and he asked me about blood color because he listened to my episode on Mythbusters where I talked about the color of blood. The color of blood is always red. Now, sometimes it's a little darker red than others. Blood that is in most arteries is oxygen-rich. And when that happens, the blood is brighter red. Blood that's in most veins is oxygen-poor. We've already used the oxygen, and that blood tends to be darker red. Now, Ben asked specifically about a nosebleed and how the blood coming out was maroon to brown. Well, there's a couple of reasons for that. The further up in your nasal cavity that the blood originates, the more mucus it's going to come in contact on its way out, and that's going to change the composition of the blood and maybe change the color. Also, the further up, the longer that blood's had to deoxygenate. So that's likely the reason why you're seeing that kind of color change. Ben also asked me about homeostasis. He was listening to episode 2, and I talked about maintaining a constant internal environment in the body. And he wanted some clarification on that. So basically what homeostasis is, it is trying to keep everything inside your body balanced and stable. We have our cells and tissues that require a safe and optimal range of a lot of different conditions in order for them to function optimally, so that we can have optimal health. That's why part of homeostatic mechanisms are temperature regulation. We need to make sure that we keep our temperature somewhere around 37 degrees Celsius. Otherwise, we can denature our proteins, which would break down our enzymes. It could break down the proteins in our plasma membranes. And that's no good. So we need to have temperature regulation to make sure we don't get too warm. Also, the colder we get, the harder it is for the cells to do their cellular activity. So we need to keep our temperature up to a certain amount. That's one example of the internal environment that we're trying to maintain, even though the outside world changes all the time when it comes to temperature. We are also looking at our oxygen levels, our carbon dioxide levels, our pH levels. We need to make sure that we have enough oxygen and glucose to make the amount of ATP that we need for our cells to do their work. So we're also concerned with our blood sugar levels. And we have mechanisms to make sure that all of these conditions are held within a specific range that is optimal for the function of our cells. pH is a lot like temperature. When our body fluids get too acidic, that can also break down the proteins in our bodies. So we can't function without functioning hormones and enzymes and plasma proteins and membrane proteins. So we need to make sure that our hydrogen ion concentration is appropriate and our body fluids are not too low or too high on the pH scale. Right? We don't want it too acidic and we don't want it too alkaline. So these are just some of the examples. You can also talk about hydration. Our kidneys, which we're going to talk about today, are regulating much of the water that was in our bodies to make sure we keep the right amount so that chemical reactions in our bodies have the watery environment they need to happen. So our kidneys today that we're going to talk about are going to work on preventing dehydration and also helping to maintain our blood pressure so that we have enough force in our arteries to get blood everywhere it needs to go in our bodies. Because that blood is carrying the oxygen and the glucose and all the other nutrients to those tissues so that they can do their jobs. So hopefully that helps. Homeostasis is not something that just kicks in when something's going wrong. homeostasis is something that's happening all the time. Our body temperatures are fluctuating all day long, and we're constantly adjusting to keep it within that specific range. Thank you, Ben, for asking those questions. I really appreciate you reaching out. Don't forget that if you have a question that you'd like me to answer on the show, feel free to send me an email at -55media@gmail.com. -55media@gmail.com. Thanks again, Ben. All right, so let's get talking about the nephron. The nephron is the functional unit of the kidney. Each kidney has over 1 million of them. It consists of two main parts. The first part is the renal corpuscle. It filters the water and solutes of blood plasma into the nephron, and the renal tubule, which is the distal region of the nephron that reabsorbs the water and solutes from the tubular fluid. The glomerulus is part of the renal corpuscle. You might have heard the term glomerulus. This is a round ball of capillaries. We talked about the blood flow through the kidney in the last episode. We discussed the glomerular capillaries, so now we're going to talk about what happens in them. The glomerulus is part of the renal corpuscle. It is the round glomerulus surrounded by the spherical glomerular capsule. The glomerular capsule is actually 2 layers with a space in between them. The layer directly attached to the glomerular capillaries is called the visceral layer, and the layer attached to the outer region of the capsule is called the parietal layer. This is a pattern we've seen several times. The cells of the visceral layer are called podocytes. Water and solutes of the blood plasma are filtered from the glomerulus into the capsular space, where it is referred to as filtrate. The filtrate then, because of a pressure gradient, moves through the glomerular capsule and leads to an outlet that carries it into the renal tubule, where the reabsorption of the water and solutes of the filtrate will take place. So when we think about our nephron, we're thinking about a series of tubules, which means little tube, after this filtrating mechanism called the renal corpuscle. Now the renal tubule is divided up into 4 segments, but only the first 3 are considered part of the nephron. The first segment, because it's the first, is called the proximal convoluted tubule, or PCT. It's called convoluted because it's all twisted up. The PCT leads to a long segment called the nephron loop. Now, nephrons all start in the cortex of the kidney, in the renal cortex, but the nephron loop heads toward the renal medulla, and some of them actually go into the renal medulla. The proximal segment of the nephron loop is called the descending limb, and the distal segment is called the ascending limb. There's a whole bunch of capillaries surrounding the nephron loops that are in the medulla called the vasa recta. Nephrons whose nephron loops go into the medulla are called juxtamedullary nephrons. Now you might look up and see someone calling those nephron loops the loop of Henle. That's an old eponym, an old term named after a person that you're not going to see in textbooks so much anymore, but you might hear a lot of people still using it. Now that ascending limb of the nephron loop gives way to the distal convoluted tubule, or DCT. The DCT is twisted up like the PCT, but since it's further along the pathway of the nephron, it's the distal version. It's also a lot shorter than the proximal convoluted tubule. Because of that, we're going to see it doesn't reabsorb as much water as we see getting reabsorbed in the proximal convoluted tubule. The distal convoluted tubule, which is the final tubule of the nephron, leads to a collecting duct, which is a long duct heading toward the renal papilla of the renal pyramid. Several distal convoluted tubules drain into each collecting duct, and several collecting ducts serve one renal pyramid. The collecting ducts converge to form a large papillary duct, and that's right at the renal papilla. The papillary duct will deliver its contents into the minor calyx. There's about 30 or so papillary ducts per renal pyramid. At that point, the tubular fluid becomes urine, and it drains from the papillary ducts into the minor calyx into the major calyx into the renal pelvis, and then into the ureter on its way to the urinary bladder. So let's think about the terms of the fluid that is being filtered out. When we first filter it out of the glomerular capillaries into the renal capsule, it's called filtrate. Then it funnels into the proximal convoluted tubule, where it becomes tubular fluid all the way through the nephron until it gets to the collecting duct and papillary duct. At that point, it becomes urine as it's flowing out of the papillary duct into the minor calyx. So at the core of kidney function is the filtration of water and solutes from the blood plasma into the nephron so the kidneys can determine which solutes and how much water is excreted as urine and what is returned to the blood plasma. The beginning of this process takes place in the renal corpuscle, like I mentioned earlier, and it's called glomerular filtration. So if we think about how much fluid we have, remember, I said last episode that it only takes 5 minutes for both of your kidneys to filter all of your blood. So 20% of your blood is going through your kidneys every single minute. So we're filtering the blood plasma out of the glomerular capillaries. Remember, the blood flow goes afferent arterial into the glomerular capillaries, then into the efferent arterial. After that, it's going to go to the peritubular capillaries, which surround the convoluted tubules and the nephron loops of cortical nephrons. Nephrons that are in the cortex, not the juxtamedullary nephrons. At that point, we have what's called the vasa recta. So let's get back to the glomerulus. The pressure gradient between the glomerular capillaries and the capsular space favors filtration, which means the hydrostatic pressure in the glomerular capillaries is higher than the hydrostatic pressure that is in the capsular space. Because of that pressure gradient, blood plasma will move from the blood in the glomerular capillary through fenestrations into the capsular space. For this to occur, water and solutes have to pass through what's called the filtration membrane, which consists of 3 barriers: the fenestrated endothelial cells of the glomerular capillaries, the pedicels of the glomerular capsullaries podocytes, and the basement membrane they share. Water and solutes must pass through all of these barriers to get into the capsular space. These membranes have filtration slits, which are negatively charged, creating an obstacle to large negatively charged ions. So they're repelled. Solutes smaller than 3 nanometers, like water, electrolytes, glucose, fatty acids, amino acids, nitrogenous wastes, and vitamins, can pass freely through the filtration membrane. Even though the filtration pores of the endothelium can be up to 90 nanometers in diameter and the filtration slits between the pedicels are 30 nanometers, the shared basement membrane consists of a negatively charged proteoglycan gel that does not allow the passage of solutes that are greater than 8 nanometers, or if they're negatively charged, like albumin. That means that blood cells, plasma proteins, large anions, and protein-bound minerals and hormones like calcium, iron, and thyroid hormone cannot get through the filtration membrane. Unbound thyroid hormone does make it through and can be observed in the urine. Also, very little albumin makes it into the filtrate. Glomerular filtration works very similar to the filtration in systemic capillaries that we talked about in a previous episode. Since the efferent arteriole is smaller than the afferent arteriole, the pressure in the glomerulus is much greater than in systemic capillaries. So let's talk about glomerular filtration pressure. In the glomerular capillaries, the blood hydrostatic pressure favoring the movement of blood plasma out of the capillary is about 60 millimeters of mercury. The hydrostatic pressure exerted by the filtrate in the capsular space, which favors the movement of capsular fluid into the capillary, is only 18 millimeters of mercury. That's a huge pressure gradient. It very much favors the movement of blood plasma out of the glomerular capillaries and into the capsular space. The colloid osmotic pressure favoring movement into the glomerulus is about 32 millimeters of mercury. But since virtually no protein enters the filtrate under normal circumstances, there is no osmotic pressure favoring the movement into the capsular space. So let's now calculate the pressure influencing the movement of fluids in the renal corpuscle. In order to calculate the net pressure of movement, we need to do some math. The net pressure favoring movement of blood plasma out of the capillary is the blood hydrostatic pressure of 60 millimeters of mercury plus the capsular osmotic pressure, which we said is 0. That gives us 60 millimeters of mercury favoring the movement out of the glomerular capillary into the capsular space. Now compare that to the net pressure favoring movement of capsular fluid into the capillary. So we take the capsular hydrostatic pressure, which was only 18 millimeters of mercury, and we add that to the blood colloid osmotic pressure of 32. That gives us 50 millimeters of mercury. So we've got 60 millimeters of mercury going out of the capillary and only 50 millimeters of mercury pushing back in. So we have a net filtration pressure of 10 millimeters of mercury favoring the movement of blood plasma out of the glomerular capillary and into the capsular space, which is what happens, and it becomes filtrate. That same pressure moves the filtrate toward the renal corpuscle's exit point and into the beginning of the proximal convoluted tubule. The volume of filtrate that is produced by both kidneys per minute is called the glomerular filtration rate, or GFR, and it's reliant upon the net filtration pressure of the glomerulus. If we're talking about biological males, approximately 12.5 milliliters of filtrate is produced each minute for every 1 millimeter of mercury of net filtration pressure. For biological females, it's about 11.25 milliliters per minute. This is called the filtration coefficient and is represented by the capital letter K with a lowercase f in the subscript. So we can calculate the glomerular filtration rate by multiplying the net filtration pressure by this filtration coefficient. So for example, we had 10 millimeters of mercury as our net filtration pressure. If we multiply that by 12.5 milliliters per minute per millimeter of mercury, we get 125 milliliters per minute for biological males, and that's their glomerular filtration rate, or GFR. If we did it for biological females, we'll use 11.25 instead of 12.5, so we'll get 112.5 milliliters a minute for biological females for their glomerular filtration rate. So now that filtrate is going to enter the tubule, where we're going to see how much of it we reabsorb back into the blood plasma. Okay, so now that the tubular fluid is in the proximal convoluted tubule, we have to start considering how much we're going to reabsorb back into the blood plasma. We call that tubular reabsorption. The PCT is the longest and most convoluted section of the renal tubule. The extensive microvilli of its simple cuboidal cells increase their surface area to maximize their capacity for absorption of tubular fluid and solutes. For these reasons, by the time the tubular fluid reaches the descending limb of the nephron loop, which means by the time it leaves the PCT, 65% of the water and solutes have already been reabsorbed into the tissue fluid of the kidney.
This is the story of the one. As a custodial supervisor at a high school, he knows that during cold and flu season, germs spread fast. It's why he partners with Grainger to stay fully stocked on the products and supplies he needs, from tissues to disinfectants to floor scrubbers. All so that he can help students, staff, and teachers stay healthy and focused. Call 1-800-GRAINGER, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
There are two routes of reabsorption: transcellular and paracellular. Transcellular means across the cell, while paracellular means between the cells. Using the transcellular route, substances pass through the cytoplasm of the epithelial cells by way of membrane proteins in the cell's plasma membrane. The paracellular route sees substances travel between the cells, through the leaky tight junctions that hold them together. The array of solutes dissolved in the water are carried through it as well. This is called solvent drag, as water, which is the solvent, drags the solutes along with it. In these ways, the water and solutes of the tubular fluid make their way to the tissue fluid of the kidneys before they re-enter the circulatory system via the peritubular capillaries. the reabsorption of water and most solutes are driven by osmotic and electrical gradients created by the reabsorption of sodium ions. So again, as usual, sodium ions, other electrolytes, they're going to come in and they're going to play an enormous role in everything our bodies do. So we're going to start with sodium ions. They're reabsorbed in each region of the renal tubule and the collecting ducts. The concentration of sodium ions is much higher in the tubular fluid than it is in the cytosol of the tubular epithelial cells. So sodium ions will move down their concentration, just like everything else does, from the tubular fluid into the cytosol using facilitated diffusion. Remember, everything moves down its concentration gradient, from high concentration to low concentration. The transport proteins used are both symport and antiport proteins. Symport means two solutes are moving across the membrane at the same time in the same direction by the same transport protein. Antiport means the solutes are moving in opposite directions. Sodium moves with glucose, amino acids, and lactate with their symport, and hydrogen ions with their antiport. That effectively raises the pH of body fluids by removing acid into the tubular fluid. So the more hydrogen ions that we put into the tubular fluid, the more alkaline the tissue fluid gets. Sodium-potassium pumps on the basal surface of the tubular cell then pump sodium ions out of the cell and into the tissue fluid of the kidney, where it is returned to the circulation through the peritubular capillaries. Under normal circumstances, all glucose is removed from the tubular fluid using sodium-glucose transporters, which are symports. It's then reabsorbed into the tissue fluid via facilitated diffusion before returning to the blood plasma. There should never be glucose in the urine under normal circumstances. Chloride ions are reabsorbed via antiport, while several other anions move into the tubular fluid. In addition to the transcellular route, calcium, chloride, and sodium ions also take the paracellular route along with potassium, magnesium, and phosphate ions. They are all reabsorbed with water via solvent drag. Now, urea and uric acid are also reabsorbed with water via solvent drag. Up to 60% of urea is reabsorbed, leaving the rest in high concentration in the urine. The proximal convoluted tubule reabsorbs almost all of the uric acid and none of the creatinine. The uric acid is then secreted back into the tubular fluid in a more distal section of the nephron. So the uric acid still ends up in the urine because it's being secreted back into the tubular fluid later. Water is reabsorbed via the transcellular route through aquaporins in the plasma membrane. You might remember aquaporins. These are channel proteins that are specifically for water. They also use the paracellular route between adjacent tubular cells. These are both driven by the reabsorption of salt and other solutes, which creates a hypertonic cytosol and tissue fluid, so water is reabsorbed from the tubular fluid. This is osmosis, right? Water is going to move from the area of low solute concentration to the area of high solute concentration. So then we have to reabsorb all of this tissue fluid that just came from the tubular fluid back into the circulatory system through the peritubular capillaries. These are the capillaries that are laced all around the proximal convoluted tubule. This reabsorption uses the same mechanisms that we see in systemic capillaries. You can review an episode from the circulatory system about capillary exchange. Due to the actions of the glomerulus and the renal tubule, when you compare the osmotic and hydrostatic pressures between the tissue fluid and the peritubular capillaries, reabsorption into the capillary is strongly favored throughout. Therefore, most of the water filtered out of the glomerulus is returned to the bloodstream. Now, since the apical surface of the tubular fluids can only fit a finite number of transport proteins, there's a limit to the amount of each solute that the renal tubule can reabsorb. If the transporters are completely saturated with solute, some solutes will pass by the transport proteins and not get reabsorbed. The transporters are solute-specific, and the maximum rate of reabsorption of each solute is called its transport maximum. For example, if the transport maximum is reached for glucose, your urine will have glucose in it. which should not be the case. So if you are diabetic and your blood sugar is very high, then a lot of that glucose that's filtered out of the glomerular capillary can't get reabsorbed because there's just not enough transporters for it. So it ends up showing up in the urine. Now, renal tubules don't just reabsorb materials from the tubular fluid, they also secrete materials into the tubular fluid, and we call that tubular secretion. Solutes in the blood plasma are imported by the cells of the renal tubule and secreted into the tubular fluid. Most tubular secretion takes place in the proximal convoluted tubule and nephron loop. So we'll start there. In the proximal convoluted tubule, the PCT, and the nephron loop, we have three main reasons for tubular secretion. 1. Hydrogen and bicarbonate ions are secreted based on the necessity to help regulate acid-base balance. 2. It removes wastes from the blood plasma, such as urea, uric acid, bile acids, ammonia, and creatinine. And 3, to remove pharmaceuticals like antibiotics, diuretics, and nonsteroidal anti-inflammatories like ibuprofen and aspirin from the blood, as well as toxins and some hormones. The distal convoluted tubule, or DCT, and the collecting duct function mainly to reabsorb much of the remaining tubular fluid, but they also do secrete some ions. The function of these regions of the nephron are largely influenced by the hormones aldosterone, antidiuretic hormone, natriuretic peptides, and parathyroid hormone. So let's take a look at these hormones specifically, because this is something you might need to know for your exams in your class. We'll start with aldosterone, which is a steroid hormone secreted by the adrenal cortex. You might be able to go back and listen to an episode on the endocrine system where you'll hear me talk about aldosterone. It targets the thick segment of the ascending limb of the nephron loop, the distal convoluted tubule, and the cortical collecting duct. When it does, it stimulates the cells of these regions to reabsorb sodium ions and secrete potassium ions. Since water and chloride follow sodium ions, the result is the retention of sodium chloride, or salt, and water. This results in a lower urine volume with a higher potassium ion concentration, but also means we hold on to water, which helps maintain blood volume and, in turn, blood pressure. Aldosterone secretion is stimulated by a decrease in the blood's sodium ion concentration or an increase in the blood's potassium ion concentration. It's also part of something called the renin-angiotensin-aldosterone system, which helps regulate blood pressure. When a drop in blood pressure is detected by the circulatory system's baroreceptors, the sympathetic response includes stimulating granular cells adjacent to the afferent arteriole to secrete an enzyme called renin. In the blood plasma, renin catalyzes a chemical reaction that converts a liver-produced protein called angiotensinogen into angiotensin 1. We do this by cleaving the 453 amino acid long protein between the 10th and 11th amino acids, leaving the 10 amino acid long angiotensin 1. In the lungs and kidneys, 2 more amino acids are removed from angiotensin 1 by angiotensin converting enzyme, or ACE, resulting in angiotensin 2. Angiotensin 2 leads to an increase in blood pressure in several different ways. First, it stimulates vasoconstriction throughout the body, including the efferent arteriole coming from the glomerulus. This increases overall blood pressure and increases the reabsorption of salt and water by the peritubular capillaries. That increases blood volume and, in turn, pressure. It also stimulates aldosterone, an antidiuretic hormone, reducing urine production and increasing blood volume. Finally, it stimulates us to feel thirsty, so we drink more water. Remember, when you increase blood volume, you increase blood pressure. The more fluid you put into that system, the higher the pressure will be. The next hormone is antidiuretic hormone, or ADH. Again, you can review this one from the endocrine system. It's synthesized by the hypothalamus, but stored and released by the posterior pituitary gland. It targets the collecting duct, stimulating it to reabsorb more water, producing less urine. ADH release is stimulated by a change in blood pressure in one of 2 ways. One is a decrease in hydrostatic blood pressure detected by arterial baroreceptors. The other is an increase in blood osmolarity detected by osmoreceptors in the hypothalamus. These conditions can be caused by dehydration, a loss of blood volume, or an increase in the blood plasma's solute concentration. If you think about something that makes you produce more urine, makes you pee more, we call that a diuretic. So this hormone is the opposite. It makes you pee less. So we call that antidiuretic hormone, or ADH. If you go back to my episode on the skeletal system, specifically the one that covers calcium homeostasis, you'll recall parathyroid hormone. When blood calcium levels are low, parathyroid hormone is released, stimulating calcium to be resorbed from the bones and put into the blood. Parathyroid hormone also targets the kidneys, stimulating them to reabsorb more calcium rather than allow it to be lost in the urine. They also inhibit the reabsorption of phosphate, increasing its loss in the urine. What that does is prevents the separate calcium and phosphate from bonding together to become calcium phosphate, which would promote it being put into the bones. But that's not what we want here. Parathyroid hormone wants to increase blood calcium. And finally, natriuretic peptides are a class of hormones secreted by the heart when blood pressure is high. Their effect is the increase in the excretion of salt and water in the urine, therefore lowering blood volume and, in turn, pressure. There are multiple actions taken by natriuretic peptides that result in a lower blood volume and pressure. They increase the glomerular filtration rate by dilating the afferent arteriole and constricting the efferent arteriole. That means that the pressure in the glomerular capillaries is going to get higher, and therefore we're going to increase how much filtrate we produce. They also inhibit the secretion of renin, aldosterone, and antidiuretic hormone. All of those things raise blood pressure. So we're going to inhibit those so we can keep the blood pressure down. And they also inhibit the reabsorption of sodium chloride by the collecting duct, which in turn decreases water reabsorption. So 90% of the water and solutes in the tubular fluid is reabsorbed by the time it leaves the nephron loop. Based on these mechanisms, the distal convoluted tubule and collecting duct continue until 99% of the filtrate from the glomerulus is eventually reabsorbed back in to the circulatory system, leaving only 1% of it to actually become urine. All right, so I think that's enough now. We're going to have to finish up the urinary system in another episode. That was a lot. So in another episode, we'll talk more about water conservation. We'll talk about how urine is released from the body, and we'll finish up the urinary system in the next episode. Thank you so much for listening. I really appreciate it. Thank you for your questions, Ben, from the United Kingdom. I appreciate that as well. I will talk to you next time, and hopefully this is helping you get your B or better in A&P. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media. Don't forget to check out my Instagram account and my YouTube channel, both called Student Help for AP. I'm posting a lot of stuff on there right now that you can watch and that will hopefully really help you understand this A&P stuff. Very special thank you out to my family, Bucks County Community College, and McGraw-Hill Education, where you can find my tutor video-based textbook alternative Anatomy and Physiology digital suite, already being used by several colleges and universities throughout the United States.